Hey everyone, welcome to another video by Simplilearn. In this video, A-star algorithm, we're going to teach you everything that you need to know about the A-star algorithm, which is a path-finding algorithm used to find the shortest distance between 2 points. So, let's get started. Before we dive into this video, let's take a look at what you can expect to learn by the end of this video. What's in it for you? First, we're gonna answer the burning question that you have in your mind. What is the A-star algorithm? Next, we're gonna take a look at the basic concept behind the A-star algorithm and the mathematical function which makes it tick. Then, we'll talk about how the A-star algorithm works with the help of a case study. Then we'll take a look at the flowchart of the A-star algorithm, using which you can implement the A-star algorithm in any programming language. And finally, we'll take a look at how the A-star algorithm can be implemented with the help of Python. So, what is the A-star algorithm? Before we talk about the A-star algorithm, let's talk a bit about search algorithms. In computer science, a search algorithm is an algorithm which typically solves a search problem. They're used to retrieve information which is stored within some data structure like arrays, stacks, trees, hash buckets, etc., or calculate the search space of a problem domain, either with discrete or continuous variables. So consider you have a stack S which contains 4 elements. Now a stack is an ordered collection of items in which you can add a new item and remove an existing item at the same time. In stacks, you can put in an item on top of another item and you can't access the elements below the top element without removing the top element first. So suppose we want to find the index of say an element in the stack, say 64. So we're gonna run it through a search algorithm to find 64 within our data structure. What this search algorithm is going to do is that it's going to take a look at the top element and see that it's not 64. It's going to remove the top element and move on to the next element. Again, it's going to compare and see if it's 64. If it's not, this element too will get removed and then it'll move on to the next element in the stack, which is 64. In this case, it's going to return the index of this element, which is at stack index 2. And using stack index 2, we can access this element. So in a way, we found the element in the stack. This is how search algorithms work. This is just an instance or a criteria on which we were searching. But using search algorithms, you can have multiple different search conditions. So you can search for every element which is below a certain number, say 40 within this stack. Or you can also search for elements which are at a certain index. So this is how powerful search algorithms are. Some examples of search algorithms include binary search, linear search, jump search, interpolation search, etc. Now, a vital aspect of search algorithms is pathfinding, which is used to find paths that can be taken to traverse from one point to another by finding the most optimum route. The A-star algorithm is one algorithm like this. It is a searching algorithm that is used to find the shortest path between an initial and a final point. So assume that you have a grid or a maze in this case. Your person is at the start and they have to reach the end of the maze, which is here at this point, denoted by this flag. Now using A-star algorithm, we can perform map traversal and find the shortest path which has to be taken within a map to go from the starting position to the end position. Now, in this case, there are many different paths that can be taken. One option is to go along the top edges of the map. The other one is to go along the bottom edges. And the shortest path, as you can see, which takes only 4 grids, is to go directly through the center of the map, cut across its diagonal, and reach the end. Now, one major aspect of A-star algorithm is that it always takes the shorter paths first, which makes it an optimal and complete algorithm. An optimal algorithm will find the least cost outcome for a problem, while a complete algorithm finds all the possible outcomes of a problem. A-star algorithm combines all of these to find all the possible outcomes of a problem, starting with the least cost solution. Now, this is what makes A-star algorithms so handy. A-star was initially designed as a graph traversal problem to help build a robot that can find its own course. And because of this, it still remains a widely popular algorithm for graph traversal. Now, let's take a look at the basic concept behind the A-star algorithm. So we already know that A-star algorithm is an optimal and complete algorithm. But another aspect that makes it so powerful is the use of weighted graphs in its implementation. A weighted graph is nothing but a graph which uses numbers to represent the cost of taking each path or course of action. This means that the algorithms can take the path with the least cost and find the best route in terms of distance and time. In path finding algorithms, for algorithms such as A-star, you're obviously going to need a graph or a map or a path to travel, right? So for computers, we feed in something called a graph. A graph contains of two major components. First, it contains something called a node. So this is a node. And it contains something called a path. A path is nothing but a line which connects two nodes. Using this, we know the direction or the path that we have to take when we're traversing through our graph, right? So first let's just make a very simple graph, okay? Right now we have two nodes, A and B. I'm just gonna add two more, C and D. Now this connection with four nodes A, B, C and D and their paths is called a graph. This whole thing is your graph. These are the graphs that these algorithms will have to travel through and find the shortest distance on. So now how do we know where we need to go in our graph? For this, we have something called a start node and an end node. So let's say our A is nothing but a start node. And our C over here, this node is our end node, right? So now we know that we have to go from this node A all the way to this node C. In this case, it becomes very easy. I can either go from A to B to C or from A to D to C. But how do I know which path is the most optimum path or the path which has the least cost? This is made very easy by the use of weighted graphs. This is a basic graph, but in weighted graphs, all these paths between nodes have a certain weight to them or a certain number assigned to them. Like say, let's just say this is 2. The cost of this path is 3. This path has a cost of 5. And this path has a cost of 1. So now, as you can see, we've assigned numbers to the paths between different nodes. These numbers tell us the cost of traversing through that path. So when I take this path between A to B, I get a cost of 2 incurred on me. And when I go from B to C, I have a cost of 3. Similarly, when I go from A to D, if I take this path, I'll have a cost of 5 and D to C will have a cost of 1. So this helps us in finding out which paths we should be taking when we're traversing from one node to the other. Now in this case, let's look at the different possible paths we can take to reach C. The first option is that we go from A to B, and this will give us a cost of 2. And then from B, we go to C, which will give us a cost of 3. Now the total cost of taking these paths can easily be obtained by finding the summation of the individual cost of these paths. So this will give us 5. All we have to do is add up the weights that each path has when we're traveling it, and we get to know what is going to be the cost of a path taken. So a path A, B to C has a cost of 5. Similarly, our path A to D and D to C has a cost of 5 plus 1, because A to D is 5 and D to C is 1, which is 6. So between 5 and 6, we know that 5 is lesser, which means that this path A to B to C is going to be our least cost path, and that is the path that we should be taking. So A-star algorithm makes use of something called weighted graphs, right? So A-star algorithm makes use of these graphs in these ways. Now let's consider that I have some other node here. Let's say that I have a node E, okay? Now B is connected to E and E is also connected to C. Let's say that the cost of taking this path B to E is 1 and E to C is 0. So now let's calculate the cost of taking the path A, B, E and C. Okay, so A to B to E to C is nothing but 2 plus 1 plus 0, which is equal to 3. When compared to A to B to C, which is nothing but 2 plus 3, which is 5, and A to D to C, which is nothing but 5 plus 1, which is 6. This path is obviously going to be the shorter path, right? But let's consider our programmer, or let's say we ourselves, don't actually want to take this path because coding for it is hard, or because it's very much isolated from the map. So we prefer to go transverse along some other nodes. And this is not a preferred node. But looking at the graph, no matter what we do, depending on how the weights are distributed, we are still going to have to go via this node. Now, to overcome this, programmers make use of something called heuristic values. What are heuristic values? So far, using a weighted graph, we've given importance to our paths. We found out which paths are the easiest to take and which paths are the ones which give us a higher cost of implementation. Now, using heuristic values, we're gonna do the same to our nodes. The heuristic value of a node in a graph attempts to capture the importance of that node's value within that graph. So the heuristic value is nothing but an arbitrary value which is assigned to these nodes based on the programmer's whims and needs. Just like how we have the weightage of paths, the heuristic value gives us the weight of a node and tells us how expensive it is to traverse through that node. It is represented by h of n. So now let's assign heuristic values to our graph and understand how exactly it changes how we traverse this graph, right? So let's say our initial start node A has a heuristic value of 1 and our node B has a heuristic value of, say, 3. Our node E, which is out of the way and which we don't really want to traverse much on, we can assign a very high heuristic value to it to ensure that it's not a path which is regularly taken. So we can assign a heuristic value of 10 to E. Let's assign other arbitrary values to the other nodes. Let's give D a heuristic value of 1 and C a heuristic value of 0. So now, as you can see, even though the paths over here take on a very short value, it would become a lot more expensive to traverse through E just because of its single high heuristic value as compared to the other nodes. How does having a heuristic value in our graph change how we are traversing? So after implementing the heuristic value to our graph, we now have two major values which come into the play. The heuristic value, which is nothing but the value of the node, and the path weight. We can represent this as g of n, which is nothing but the weights in our weighted graph, right? So as you can see, when we're traversing from one node A to a node B, we're gonna have to consider both of these values. So the cost function of a graph, or the total cost of taking a path, becomes the value of the path weight, which is given by the weighted graph, along with the heuristic value, which is assigned by the programmer or by you yourself. And this here is the basic function behind our A star algorithm. This is the formula that our A star algorithm works on. So initially, the A star algorithm will calculate the cost to all of its immediate neighboring nodes and choose the one which is incurring the least cost. This whole process will repeat until no new nodes can be chosen and all the paths have been traversed. And then you should consider the best path among them. And how do you find the cost function? Again, you're just going to add up the heuristic value and the path value that you've taken. Now g of n, which is the path value, is nothing but the cost of traversing from one node to another. Very obviously, this will vary from node to node. Whereas h of n, or heuristic approximation of a node's value, is not a real value but an approximation cost that you or some other person has assigned to various nodes. Now that we know the basic concept behind the A star algorithm, let's take a look at how exactly the A star algorithm works with the help of a case study. So now let's take a look at how the A star algorithm works. To do this, we're first going to consider a weighted graph, since A star algorithm uses weighted graphs to make its calculations easier. So consider this to be our weighted graph. We have a node A, a node B, a node C, a node D, and a node E. Okay. Now node A is connected to node B. Node B is connected to node E. Node E is connected to node D. D is connected to C, and C in turn is connected to A. C is also connected to B, and A is also connected to E. So now let's assign the path values to all the different paths in our weighted graph. Let's say A to B has a path value of 1, B to E has a path value of 6, D to E has a path value of 5, C to D has a path value of 9, A to C has a path value of 10, and A to E has a path value of 2, and this has a path value of 3. Now let's assign heuristic values. Let's give A the heuristic value of 2, B the heuristic value of 5. Let's just give this a 7. Let's make this 4. And let's give C a heuristic value of 0. Okay. So now this is what a weighted graph looks like. From the basic working, you already know that the cost function of your weighted graph is nothing but the path value along with the heuristic value. So let's now say that A here is where we have to start from, and E is our target node. Okay, and this is where we are going to be starting from. Now A is our starting node. So there are three different paths that we can take: A to B, A to C, or A to E. So first let's consider that we take A to B, okay? The first thing that you have to consider is the heuristic value of A itself. So f of A is the first value that you're going to be considering, right? Now f of A here is going to be the path value plus heuristic value. Now because A is the starting node and there's no other node leading up to it, it is the parent node itself. So the path value here is going to be 0 because there's no path leading up to it. It's the starting node, and the starting node always has a path value of 0. Next, we're going to add the heuristic value of A. In this case, 2. So 0 plus 2. So f of A is 2. Right? So this is the first node that you've considered. Okay. Now, after taking node A, we have three different options: A to C, A to E, or A to B. So the cost function of taking the path A to B is going to be, so now let's find the cost of taking the path A to B, right? A to B, so you have to add the graph node value plus a heuristic value. The weight of taking the node A to B is nothing but 1, and the heuristic value of B is 5. So this is going to give us C. Next, A to C. Sorry, starting. Next, let's look at the cost of taking the path A to E, right? F of A to E. So this is going to be 2 because the cost of taking this path is 2, along with the heuristic value of E, which is 7. So this is going to be 9. And let's look at f of A to C. Now the cost of taking this is going to be 10 plus the value of C, which is 0. So this is going to be 10. Now the way how A-star algorithm works is it will calculate the cost function of all the neighboring nodes and go with the node which has the least cost function. In this case, the node being B. So we're not going to take this path or this path because the cost function value is way more than the cost function value of f of A to B. So after A, we are going to be at node B. So right now, this is the direction that we've traveled in. Now when we're at node B, to reach node E, we have two different options. We have two options that we can take. We can either go from B to E or we can go from B to C. Okay. The goal of A-star algorithm is to always minimize the cost of the path that you're taking. So using this in mind, let's calculate f of B to C, which is going to be nothing but the cost of the path from B to C, which is 3, plus the heuristic value of C, which is 0. So this is going to be 3. Next, let's calculate the cost of B to E. Now this is going to be again nothing but the path value, in this case 6, plus heuristic value, in this case of E, which is 7, which is nothing but 13. So again, as you can see, this is the correct path to be taken. And we are not going to be taking this path because its value is way too high. So the next path that we're going to be taking is this path, B to C. So now we're at node C. From node C, we can either go to A, which is not possible because we do not go back in the direction that we came from, to B, again, that's not what we're going to be doing, or to D. So the only option that we have available is to go from C to D, right? So what we're going to do is we're going to find the cost of going from C to D. Again, this is going to be the value of the path, which is 9, plus the heuristic value of D, which is 4. The cost of traversing this path is 13, but we don't have any other path available to us because this path has already been closed. You can't backtrack in A star algorithm or go back to the path where you came from. And again, we've already considered A to C before, right? Like over here, we've already considered A to C and we've already ruled it out. So again, this is not a path that you can take. So what we're going to be doing right now is that we're going to be traversing from C to D. And the cost of taking this path is 13. So now, this is the path that we're taken from C to D. We're at D now. At D, again, we can't go back to this path. We can't go back to C. The only way we can go is E. So we're going to consider f of D to E. And this is going to be, again, the path that you're going to take from D to E, which is 5. Plus the heuristic value of E, which is 7. This whole thing is going to be 12. Now, once we're at C, our A star algorithm is going to check if this is the target node. And lo and behold, it is. So we've traversed from A to E. Let's see the path we've taken. First, the starting node that we started off from was A. From there, we looked at the cost of taking A to C, A to E, and A to B, and finally we settled for going from A to B. From B, again we consider the paths B to E and B to C. We cannot consider A to B because this path has already been traveled on and it's already been considered before. Now, after considering B to E and B to C, we found that B to C was the shortest path. From C, we didn't have any other option. We couldn't backtrack or go back to B, and we couldn't go to A because this path was already been considered and already it has been ruled out. So the only path we could take from here was to D. And again from D, the only path that we could take was to E. So now let's look at the path that we've taken while using our A star algorithm. We started off at the node A. This was our starting node. From node A, we had 3 options. We could go to node B, to node E, or to node C. After considering all of these options, we realized that A to B was the path of least cost that we could take. Once at B, we considered 2 paths, B to E and B to C. And we found out that B to C was the path of least cost. From C, there was no other path we could take. We cannot go back to the node we came from, which is B, because A star algorithm does not support backtracking. And we couldn't go back to A either because this path had already been considered and we'd already ruled this path out, right? So the only path we could take was to D. Now, once we arrived at node D, the only node that we could travel to again was E. So using A star algorithm, this is the final path that we've taken to traverse from our start node A to our target node E. And with the help of this case study, we've also explained to you exactly how the A star algorithm works. We use the path values and the heuristic values to find the cost of taking different paths available to us at each node. And then we take the path which has the least cost among all available paths. The same process will continue until we've reached the final target node. And again, remember, you cannot go back on the path that you came from, or you cannot go on a path which has already been considered. So now you know how the A star algorithm works. But what is the flowchart of the A star algorithm? Now, a flowchart is a picture of the separate steps of a process in a sequential order. It's basically a generic tool that can be adapted for a wide variety of purposes, and you can use it to describe various processes. In this case, this is the basic flowchart of the A-star algorithm. It tells the direction of control flow within the A-star program, and using this you can implement A-star algorithm in any desired language of your choice. So the first step of our A-star algorithm is to initialize the start node and put it in an open list. Now in this algorithm, we're gonna first create two lists, an open list and a closed list. The open list will contain all the nodes that have been visited, but their neighbors have yet not been explored. On the other hand, the closed list contains nodes that along with their neighbors have already been visited. So the first node or our starting node is going to be put in an open list because we're still exploring it. Then we're going to calculate the cost function of the starting node. From here onwards, we're going to remove this node from the open list and put it in the closed list since we've already visited it and calculated its cost function. If we're also looking at the neighbors which are surrounding this node, or if this node has many different nodes around it, then we're going to calculate the cost function for those nodes too and save the index of the node which has the smallest cost function f. Next, we're going to look at if the node we're currently on is a final node or a target node. If that's the case, we're going to terminate the algorithm and use pointers of all of our nodes to get the desired path. If that's not the case, then we're going to look at the successive nodes of n, or all the nodes which come after this node which are not in the closed list. We're going to calculate the cost function of each of these neighboring nodes, remove them from the open list as they're not already in the closed list, so they're obviously going to be in the open list. So we're going to remove them from the open list and then we're going to put them in the closed list. And again, we're going to save the index of the neighboring node with the smallest cost function. And then this process is going to keep repeating over and over until we've reached the target node, which is where our program will get terminated. So basically what we're doing is we're going to a certain node, calculating the cost function for that node, looking at all the successive neighboring nodes of it, and going to the neighbor which has the least cost function. Now this process will again get repeated. So from this neighboring node, we're going to find all the other nodes which are connected to it. And then we are going to go to the node which has the least cost function. So using this, we're going to hop from one node to another depending on which node has the lowest cost function. Once this is over, we're going to again take some other node and we're going to repeat this process until we found all the possible paths to a final destination node. And in this way, the A-star algorithm is not only going to find the shortest path, but it's also going to find all possible paths. Now, let's see how the A-star algorithm can be implemented with the help of Python. In this demo, we will use the A-star algorithm to find the least cost path between various nodes in the weighted graph which is shown below. So in this graph, as you can see, we have 6 different nodes A, B, C, D, E, and G. The weights of the paths between these nodes is denoted by these numbers in black, and the heuristic values of the nodes itself are denoted by the numbers in red. Now using these values, we can find the shortest distance between any two nodes. Let's see how we can do this with the help of Python. So now let's start by creating a class for the A-star algorithm called the A-star algo. Now in this algorithm, we're going to have to describe the open and the closed list. And to do this, we're going to be using two sets. So our sets are our open list and our closed list. We'll also be using two dictionaries, one to store distance from the starting node and another for parent nodes. And we're going to start by initializing them to 0. The open set is going to have the start node already in it. Now, we all know that the distance of the starting node from itself is 0 itself. So we're going to initialize the distance of the start node to 0. And we also know that the start node is the root node and it has no parent nodes. So the start node is its own parent node. The first step of initializations is to put the start node in the closed set to set the distance of the start node to itself as 0 and to set the start node as its own parent node. Now that we're done with the first couple of initializations, let's move on to finding all the neighboring nodes. So now we're going to have to find the neighboring nodes with the lowest value of the cost function. We also have to code for the condition of reaching the destination node. If this is not the case, we're going to have to put the current nodes in the open list, and if they're not already in it, then we're going to set their parent nodes. So that's what we're going to do. First, we're going to find the node with the lowest cost function. We're going to take the entire open set, and while the length of it is greater than 0, or basically while we're not at the parent node, we're going to loop through it. We're going to go to all the neighboring nodes of the open node, and then we're going to find their cost function. Now here, this is the function that you're going to use to find the cost function. Now here, what we're going to do is we're going to calculate the heuristic value for n, and if the cost function of n is 0, or if its cost function is less than the cost function of its neighboring node, then we're gonna move on to the next node, which is v. Now if n is equal to the stop node, or we've looped back and come to n itself, then we're not gonna go ahead, or we're gonna exit this loop and we're gonna move on to some other node. Otherwise, if the neighbor has a lower g value than the current node and is in the closed list, we're going to replace this new node as the neighbor's parent. And that's what we're doing here exactly. Now, if the neighbor is not in both the lists, then we're going to add it to the open list and set its g value. And that's basically what's going on here. So let's run this for the A-star algorithm. Now we're going to define a function to get the different neighbors and their distances. Next, we're going to create a function to store the heuristic values and retrieve them as and when required. Now we're going to describe our graph here. So these are all of our nodes and the nodes that they're connected to, along with the weight of their paths. So here A is connected to B and the weight of this path is 2. A is also connected to E and the weight of this path is 3. In the same way, B is connected to C and the path has a weight of 1, and B is also connected to G and the path has a weight of 9. So here, this is what we're going to do to describe our entire weighted graph. And then we're going to finally call our A-star algorithm and give our starting node and our final node. And it very quickly finds the path between our starting node and our final node. And over here, as we can see, the best path to take would be from A to E to D and finally to G. And that brings us to the end of this video on the A-star algorithm. We hope that this video was useful to you and that you not only learned A-star algorithm in depth, but also how to implement it in Python. And we also hope that you enjoyed this video. If you did, a thumbs up would be really appreciated. Also, here's your reminder to subscribe to our channel and click on the bell icon for more on the latest technologies and trends. Thank you for watching and stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.